All right, so let's work through deriving the ridge solution. And so you did this in the last application exercise, and so let's just go through those steps now. All right, so as a reminder, the ridge regression, the thing we're minimizing is the residual sum of squares plus this penalty term, lambda times beta transpose beta. And remember that beta transpose beta, that's the same as writing the sum of beta squared. So this is just writing that same formula, the sum of beta squared, but kind of in matrix form, or in this case, vector form. We write that as beta transpose beta. So the first thing I'm going to do is just plug in what residual sum of squares is here. So the residual sum of squares, remember, is just y minus x beta transpose times y minus x beta. So y minus x beta is the residual, and so if we want to take the sum of those squares, we just multiply that transposed by itself. All right, so we've plugged in the residual sum of squares. We've got our penalty added on here. The first step is to FOIL, the same as we did when we were trying to derive beta in the least squares or in the linear regression case. So let's go ahead and do that foiling. So I get this y transpose y because this transpose here gets distributed to this y, and then I multiply that by the y. That's the f in FOIL, the first. And then the next is going to be, well, if we do the outer, that's going to be this guy and this one, so that's going to be x. Well, the transposes flip the order, so it's going to be beta transpose x transpose times x transpose beta, and so that's what this term is here. And then the inner is going to be, oh, I apologize. That's actually, the outer is going to be this one here, this y times x beta. So that's going to be the y times x beta. The inner is going to be x beta, or beta transpose x transpose times y. And so those two terms combine. And why do those combine? Well, if you recall from our previous lecture when we learned about how to derive the beta coefficient, or the beta hat in the least squares estimator, this is the beta transpose x transpose y is a scalar. It's always a scalar based on the dimensions of each of these different vectors and matrices. And when you transpose a scalar, you get the same thing. You get that same scalar back. And so because beta transpose x transpose y is the transpose of y times x beta, we can combine these two terms here. So that's what we've done here with this -2. Okay, and then the last is that the one that I initially accidentally said was the outer. The last term is just this x beta and this x beta, which come to this. And then, of course, we still have this penalty added on. All right, so we foiled this. What is the next thing we do when we're trying to derive a beta coefficient, or the beta estimate? We take the derivative. So let's take the derivative of this whole thing with respect to beta. And so here it is. So of course, if you take the derivative of y transpose y with respect to beta, it's just going to be 0, so that goes away. If you take the derivative of -2 beta transpose x transpose y with respect to beta, that's going to be -2 x transpose y. If you take the derivative of beta transpose x transpose times x beta with respect to beta, that's going to be 2 times x transpose x times beta. And if you take the derivative of lambda times beta transpose beta, that's going to be 2 times lambda beta. So here's our derivative of this quantity that we're trying to minimize. What is the next step we do? We are going to set that equal to 0, and then we're going to solve for beta. So all I've done here is set this derivative equal to 0. And now let's get to solving so that we can figure out what beta is. So this is just simple algebra. First, I can get rid of all these 2's. Since I have 2's everywhere, let's divide both sides by 2. And I end up with 0 equals -x transpose y plus x transpose x beta plus lambda beta. And now I'm going to move this -x transpose y over to the left side of the equation. And now I'm going to pull out the beta. So I've got a beta in both of my terms here. So I can pull it out to the outside. So I end up with x transpose x plus lambda times I times beta. Why did I stick this I in here? Well, lambda is just a scalar. And so in order for these two things to be able to be added, I can add in that identity matrix, which basically will stick the lambda on the diagonal of this matrix, which is going to be equivalent to adding that lambda term. And multiply that by beta. And now we just need to move this quantity over to this side. And of course, we know in matrices, the way to move something from one side of the equation to the other is to take the inverse. And so now we end up with x transpose x plus lambda I inverse times x transpose y equals beta. So this is our estimate for ridge regression, for beta for the ridge. And that's exactly what we showed in the previous class. And so this is the final derivation.